Just to introduce back again Dr. Phil Renforth, who's going to discuss removals from the iron and steel industry.
Yeah, thanks, Simon. So in addition to helping to coordinate the science behind the programme, I'm also the PI on the one of the smaller topic-specific projects. It was a project we put together between myself and a collaborator, Professor Will Mays at the University of Hull, and I'll also involved on the project with James Campbell at Heriot-Watt and Hugh Pullen at Cardiff University, and apologies, but I left Helena Gomez, who was the postdoc at the University of Hull. Within this project, we were thinking about facilitating the reaction that Idong touched upon in his presentation. That's the sort of carbonation of silicate rocks, where CO2 is reacted with a mineral material. But of course, we're interested in anthropogenic materials, particularly the slag from the iron and steel industry, but there are other materials out there that do the same sort of thing, and those are byproducts from the mining industry, which Idong touched upon, byproducts from the aluminium industry, and then also products from the cement industry, the lime industry, and production of caustics. One output from the project was essentially assessing what the potential CO2 removal of these materials were projected into the future. So at the moment, estimates are around a gigaton of CO2 per year potential. And that sort of is consistent with a lot of other other reported numbers in this space. But we projected going forwards through to the end of the century, and actually, because we increase a lot of these materials to meet material demands of future populations, the potential of these materials goes up, and it might be something on the order of 3 to 7 gigatons of CO2 per year. So that's an enormous potential from alkaline materials such as these. And it certainly warrants us investigating them. But our focus was on slag from the iron and steel industry. It's produced as a byproduct at the moment. And we did two things, really. The first was to look at a legacy deposit. This is Consett in the northeast of England. There was a steelworks operating there from 1840 through to 1980. And this is, you can see the slag deposit that was put down during the steelworks operation. It's about 30 million tons of material. And that's what it looks like today. So a lot of people who live in the area have no idea that that's a slag heap, and they walk their dogs across the top of it. So our idea was to go and take a look at that to see if we can see CO2 uptake within that environment. What you can do is you can go to the outflow of the water coming off from that deposit, and it's actually quite a remarkable environment. I mean, there's not many places in the world that are pH 11.5. The waters are pH 11.5, and they have been for the past 40 years. It's a pretty interesting environment. You say that, so the waters coming out of the heap are really high pH. They contact the atmospheric CO2, and immediately the pH drops, and they form carbonate minerals in the outflow. And sort of by 100 meters downstream of that, the pH and the chemistry is almost back to background levels. So it's quite a massive or rapid attenuation of the effect. What we wanted to do was see what was going on inside of the heap and looking at the solid material within the slag. So we commissioned some drilling work that we did a few years ago, and we drilled 3 boreholes and sampled the solid material. And I suppose maybe just to cut a long story short from that work, there's actually not that much CO2 being captured in the middle of the heap. And it's kind of what we expected because of the pH of the waters. But I mean, it's good, in some ways, good confirmation of what we anticipated. And you might think that that's a disappointing result, but actually it's quite a positive result in that you think of all of the legacy deposits that we have around the world. We have produced slag for a really long time. there's a good reason to believe, or at least evidence now, that those legacy deposits could become a resource for CO2 removal. So that there's potential for a lot of CO2 capture. So as part of the project, we looked at the UK's potential for that. This is work led by colleagues at the University of Hull. But essentially, the findings are that there's about 190 million tons of slag legacy deposits in the UK. It's roughly about half of what we produced historically. So, the other half was material incorporated into infrastructure, into buildings, as secondary aggregates. But we think that there's about half of that material is still deposited in places in the UK. And that has a cumulative capture potential of something on the order of 60 to 140 million tons of CO2. So, within the UK's context of CO2 removal, if we wanted to exploit that, then maybe it's not huge. The UK's targets for CO2 removal are on the order of 100 million tons of CO2 per year by 2050, give or take some. So maybe this could make us an important contribution, but not a massive one. But I think what the real interesting results of this is that the distribution of this resource is highly asymmetrical. It's located in former industrial or deindustrialized communities, and particularly in the north of the UK. So that obviously has a lot of interesting political aspects to it, and that if we wanted to exploit that resource, we'd need to invest quite a lot into those communities to do that. So I'm trying to sort of claw back a bit of time for us, so we can have a bit of discussion. So just to summarize, I think what our key findings are. The alkali materials globally have a really large potential. Slag is part of that, as is demolition waste and mine wastes, etc. This, in terms of net negativities of this material, it changes depending on whether you're looking at legacy deposits or whether you're looking at contemporary production. But this is most effective when you're decarbonizing the industry that's producing them. So, the steel industry is already under pressure to do that. If they decarbonize rapidly, as well as use slag for carbonation, it is possible, although potentially unlikely, that you can show a pathway to net negativity for steel. But that wouldn't be possible without decarbonization of that industry. And the same sort of story is true for other industries that produce these alkaline materials as well. So the outcomes from our work at Concert suggest that contemporary and historic management practices for slag are not sufficient to maximize CO2 removal, and that we need to change what is happening to maximize that removal potential. Exactly what that looks like is something that is part of ongoing research, and how do we engineer these systems for maximizing CO2 removal. And I suppose the final point is that the legacy deposits may retain considerable potential, obviously not just in the UK, but globally as well. So, and that could be exploiting that CO2 removal potential could be coupled to other co-benefits like land reclamation, which is already happening at a lot of these sites in the UK as well. So I suppose I'll just leave it there, and thanks a lot for your attention.